Thank you very much. So I've seen really some good solutions to the problem of like, you can't look back on slides if they're just slides. One different solution is you can just look at my slides and have them open in front of you. And I'll trust you that you're not like actually watching the World Cup game. If there one happening now, not sure. Today we're going to talk about theta functions and acyclic affine type. I'd like to thank the organizers for inviting me to do that. And very happy to be here. I'll talk about scattering diagrams, what they are. Do a really quick reminder of cluster algebras, which I think can probably go pretty fast by this point. I'll tell you about theta functions and particularly the results on theta functions and affine type. I'll talk about some of the tools that are involved. And then there's going to be some combinatorial details that I won't have time for, but they're in the slides because I'm always more nervous about running out of material than running out. Don't worry, I also will stop. But honestly, the tools, part of the tools is also under the heading of things I won't have time for. But before I go on, late breaking news, I am, well.
How many words?
Oh my goodness, I have no idea, which is part of the problem. There were only 2 chapters, subsections, yes. But anyway, I was pleased actually that basically all of the other participants had the good sense to have a much shorter abstract than that. And so let's go on. So the overview of the talk, cluster algebras came from the study of total positivity, and then, as you know, found a lot of applications and connections everywhere. Everywhere might be a tiny overstatement, but more recently there's been a connection with scattering amplitudes in physics, what happens when 2 particles collide. Scattering diagrams, despite the similar name to scattering amplitudes, are a different thing, but they arose in mirror symmetry, and they were applied by Grossack and Keel and Kontsevich to prove some long-standing structural conjectures about cluster algebras. Somehow, one of the most meaningful pieces of it is that you have a cluster scattering diagram, and I'll say what some of these words mean to some approximation, but you get theta functions, and theta functions are they include the cluster monomials. Maybe it would have been better to have an inclusion going cluster algebras included inside theta functions, but okay. In principle, if you give me an exchange matrix, I can give you constructively a cluster scattering diagram. But in practice, it's really an existence theorem because you would have to just do so much at a tiny level everywhere that to actually construct this thing. So and to make theta functions, you are summing over things called broken lines. Again, in practice, this is a completely combinatorial description of what theta functions are, but you have to find the broken lines and you have to prove that you've found them all. And so you need combinatorial models. When Salvatore Stella and I were working on some of the very earliest aspects of this about 10 years ago, the GHKK paper came out on the scattering diagram stuff, and Salvatore said, I think they've closed the field because they proved a lot of things that people have been thinking of. But in fact, they sort of opened the field because combinatorial models were needed. So that's one of the things I've been thinking about a lot before that exists. So in this talk, I'll talk about results on theta functions and affine type and some of the models and tools needed to prove. Okay, so quickly scattering diagrams. I would like to ask you to sort of let your eyes unfocus on the top part of the slide. It's all there if you like. But we have Laurent monomials in some x's, x1 through xn. We have Laurent monomials in some y hats. The y hats are really, if you've seen cluster algebras before, you know what I'm talking about. If not, it'll be okay to just kind of let them be just symbols. And you can specify a Laurent monomial as, x2 a vector. Integer vector. What's a scattering diagram? Scattering diagram is a collection of walls. Each wall is a pair, sort of a fraktur D, which is a codimension 1 cone, and linear cone, so everything's at the origin. And then there's a function f, which we call a scattering term on each wall, and the scattering term is a formal power series in these y hats. And I'm setting this up because I wanted to match cluster algebras for terminology. There's other ways to set this up, different variables to use. Okay, and then some details that just really quickly. Each wall is normal to a primitive positive integer vector. So that puts a lot of limitations on where those walls can be. And actually, each scattering term is a univariate formal power series in some Laurent monomial. Actually, monomial in the y's with constant term 1. And there's a finite condition, and basically the finite condition adds up to anything we want to say if we do limits of formal power series will work. Okay, so I'm sweeping lots of details under the rug, and part of the reason is because they're elementary. There are just too many little details to tell you, it would take too much time. There's nothing hard about the details I'm skipping here. When you cross a wall in a scattering diagram, you sort of have this some Laurent monomial in the x's and the y hats, and you cross a wall, something happens to it. Okay, it gets replaced by itself times some power of the scattering term and whatever it is. Okay, and now you can think about, okay, I'm going to walk through my scattering diagram. I'm going to cross some walls. Okay, then going to just do that action on all the monomials I have, all the formal power series I have. Consistent would mean it doesn't really matter what path I took from here to here. It just matters where I started and where I ended. So you want a consistent scattering diagram. Again, this is just, believe me, but this scattering diagram on the left is not consistent, but it turns out that if we add one more wall, then it's consistent. Okay. The theorem of Gross, Hacking, Keel, and Kontsevich is, given an exchange matrix, there's a unique, consistent scattering diagram that satisfies two properties. And again, I guess I got details about one of the properties, but just let your eyes unfocus about what outgoing is too also. It contains all the coordinate walls, the full hyperplanes, the full coordinate hyperplanes with somehow the simplest possible non-trivial scattering term that you can imagine. And then you have to put in more walls to make it consistent, that you have this limit on which walls you can put in. They have to be outgoing, and it's actually there. It has to do with them containing some vector. Okay, so for example, this scattering diagram is consistent, and the point is, if I only had the coordinate lines, it wasn't consistent. But I added one wall, and it turns out this is outgoing, and so this is the cluster scattering diagram. Theta functions. Again, no detail. The details aren't hard. I mean, the details are hard in the sense that you have to, do them in computations over and over again, but they're elementary, right? So I want to tell you what a theta function is in really rough terms. This is a scattering diagram. This is a cluster scattering diagram for that exchange matrix there, type G2 if you like. If I wanted to make a theta function, well, it's indexed by a vector, and this vector, I just have a basis that's row 1 and row 2. So this vector is -2, 3, if you like. I'm going to start with a bunch of, I need to choose a point. It doesn't matter. I need to choose some point in the interior of the positive quadrant, in general, positive ortho in higher dimensions. And I'm going to take a bunch of lines coming in from that direction. So they're coming out from infinity, but they're coming from that direction. Okay. Broken lines, and they break, in other words, they bend, right? So they're allowed to bend on walls or not, according to some rule that's just, it's elementary. And so what I'm going to do is I'm going to figure out, I'm going to decorate those walls with this monomial that comes from the vector. I'm going to figure out all the ways that they can bend according to the rules and end up at that point P that I chose. And as they bend, the monomials change. So that in the end, there is a list of broken lines with sort of their last monomial, the monomials they had when it came into P. I add up all those monomials, that's my theta function. Okay, so it's sort of zero details, but that's the kind of beast that this is. Okay, so if I want to compute a theta function, I need to be able to say, okay, I have found the collection of all possible theta functions that do that. Okay, if you multiply theta functions, it's true that every product of theta functions is I don't know why I bothered with possibly infinite. It's a linear combination of theta functions. I have lived in worlds where it's not infinite, so just a linear combination of theta functions with coefficients in these y's. But the structure constants, if you want to figure out what the structure constants are, I mean, aside from just actually computing the theta functions and then working it all out, you have to find pairs of broken lines. So you find all pairs of broken lines that satisfy certain conditions, and those pairs specify a theta function and also a monomial in the y's, and so you sum up, that monomial times those theta functions, and that's what your product is. So again, even less detail. If you want to multiply theta functions, you need to not only just find out all broken lines with certain conditions, you have to find all pairs of broken lines that satisfy.
These are deep numbers.
What's that?
They're deep numbers as opposed to some rational functions.
No, they are, well, no, we really wanted to be rational functions in the x's and y's and whatever, yeah. When you do the surfaces model, it's nice to turn them into numbers because then they're actually lengths and things. But I'm just happy to have them be indeterminate. Yeah, other questions? All right, so that's what I need to do to find structure constants. And this is to recap. So scattering diagram, you've got these cones called walls, and they have scattering terms. You have this idea of wall crossing. You need some things to be consistent as you cross along walls. It doesn't matter which way you went. There's a cluster scattering diagram, which somehow is a nice one in a way that we'll show in a second. Theta functions are sums over broken lines, and if I want to multiply theta functions, then I need to somehow sum over all possible pairs of broken lines satisfying some certain conditions. Again, the conditions are always elementary, but I don't want to log down with detail. Maybe it's a pop-up question, but I've said so little. But go ahead.
I'm just wondering about the wall crossing. Does the wall crossing change like the monomial or the scattering term of the specific wall?
No, that's a good question. The scattering diagram is once and for all, it is itself. And then it's a question of what does that scattering diagram do to things as I cross through? Yeah, good question. Other questions? So let's talk about cluster algebras quickly. I think I can go really quickly. There's initial seed, there's an initial cluster variables, a variable. I guess some of you spent a big part of last week thinking about this. And lots of us have heard about this week, but there's this mutation. It's an operation that takes a seed and gives a new seed. There's n directions of mutation. Mutation sort of takes one cluster variable out, puts in another one, and also changes the exchange matrix. Okay, and it's an involution. Okay, I'm doing exchange matrices. You've seen them a lot with quivers. You just sort of take the most natural matrix that you can associate with the quiver. This is the same. All right. If you're in the know about this, everything I'm saying secretly assumes principal coefficients, and I'm not even going to say anything about coefficients. Not the y's are coefficients. I guess I said something about coefficients, but okay. The y's are coefficients somehow. But the things that I say are true carefully about principal coefficients, and then if you want other coefficients of geometric type, then you can do that too. But you have to state things a little bit differently. Okay. So this is sort of the cartoon that I like to do. Actually, I think that I stole this cartoon from Sergey at some point. We wrote a paper together or something, and one time he told me I could use this in a talk, and I haven't asked again, so I hope it's okay. But this is just the cartoon, right? I've got this seed, I've got the cluster variables. I throw out x3. There's a way that I get a new one here. Now I've got x1, x2, and x3 prime, and I've also changed my exchange matrix, and I go on forever. The cluster algebra for that initial seed is just the collection of the ring generated by the collection of all these cluster variables. Okay, so here's how the two things I've talked about so far connect. First of all, I guess this is not having to do with scattering diagrams yet, but a theorem of Homogeneous the cluster algebra 4 says that each cluster variable is a Laurent monomial in the x's, and I'll write x, the variable's v, so I'm going to write x to the g of v. G of v will be called the g vector of v times a polynomial in the y hats. Okay, so that's just good basic knowledge about what these things look like in principal coefficients, or really in other coefficients. You can do more or less the same thing. The theorem from Grostak and Keel and Kontsevich is okay. So there's some geometry you have to think about in 90 dimensions or whatever. But you have all these walls in your scattering diagram, right? They're codimensional on cones. You can imagine them sort of cutting space into different regions, and it turns out that they cut space into a fan. Okay, meaning a collection of cones that intersect nicely in the ways that we're used to. Part of that fan that's cut out by the cluster scattering diagram is the G vector fan. And what's the G vector fan? Well, you've got all these cluster variables, and each one has a G vector. So let's let each G vector span a ray, and then the cluster variables come in groups of n. And so let's take the n cluster variables, their G vectors, and let that span a cone. The non-negative linear span of those vectors is a cone. put all those cones together. It was a conjecture for a while, maybe, I guess, really became a theorem with this GHKK paper, that was always a fan. So that's the G vector fan. It's somehow sitting inside the cluster scattering fan, right? So that's already the first indication that something really good is happening if you want to understand cluster algebras using cluster scattering diagrams. A cluster monomial. Let's look at this picture. And this just for no good reason, I guess. I don't know what these details will mean to you, but I've written all 5 cluster variables in this. This is type A2, if you like, or just a 2x2 exchange matrix with a 1 and -1 on the a quiver with 1 arrow, right? 2 vertices, 1 arrow, if that will work too. But see, you can see the fan here. This is the G vector fan here is everything. So I've got a cluster with x1 and x2. I can think about monomials in x1 and x2. I've said Laurent before, but I just mean honest monomials, positive exponents in x1 and x2. Those are called cluster monomials. But also here, there's also another cone. I can take monomials, or there's a cluster with x2 and this more complicated thing. I can take monomials in those 2 functions. Those are cluster monomials. And the reason that GHKK had anything to say about cluster algebras is because any cluster monomial is a theta function, specifically a theta function for its G vector. There's some funniness with that if you don't do principal coefficients, but we can talk about that later if you'd like. So the other thing that's in GHKK, well, among many things, but the thing that I want to point out is that theta functions are a basis for what they'll call a canonical algebra. And it often agrees with the cluster algebra, and maybe more often, if this says something to you, more often agrees with the upper cluster algebra. So somehow this scattering diagram machinery has captured a lot about cluster algebras. Okay. I've already told you what theta functions are if lambda is a vector in the G vector fan. It's a cluster monomial. I keep saying vector. I think I definitely always mean integer vectors when I say this. So if lambda is a vector in the cluster fan, those theta functions are cluster monomials. But the theta functions form a basis for this thing that we want to understand. And some of those theta functions are indexed by vectors that are outside the G vector fan. What are those? How do we understand those? That's kind of the question that I'd like to understand. I think in lots of cases, we can't even really understand what all the cluster variables are. But so I've been dealing in cases where we can understand what all the cluster variables are, but what are the theta functions? And again, why? Because we want to know that whole basis. Okay, now this is just a tangent, but this was what I was trying to decide if some of this is really new, like finishing writing it last week and not quite done. So I decided not to talk about this, but I decided I would let myself take 2 minutes for a shameless plug for it. There is another way to get cluster variables, cluster monomials, out of the scattering diagram. Okay, you can define something called a return function for lambda. Again, lambda will be the G vector, the thing we want, right? But we start at lambda and apply wall crossings to x to the lambda along a path to the positive cone. If you're in the know about this, what I'm doing is I'm taking the monomial x to the lambda. I'm applying a path ordered product that sort of in the limit comes from lambda and then goes back to the positive cone. Okay. If you do that, there's some basic stuff from like Karl Pumperlet and Siebert, I think, and then sort of repackaged in Roshack and Keel and Kontsevich, and you can just work out the cluster monomials are these what I'll call return functions, just applying a path ordered product to the monomial. So it's sort of returning in 2 senses, right? You started with x to the lambda as a monomial. You also started at lambda if you're returning home to the positive chamber. I don't know that anybody wrote this down ever. It was kind of fun to notice this. I suspect that Roshack and Keel and Kontsevich would have said, "Oh yeah, of course that's true," but they didn't write it down, and it was super exciting to be like, "Wait a minute." Playing with examples. Always play with small examples. Don't always let AI do it for you. Play with them yourself, and you might notice something that will be really fun. Okay. Anyway, theta functions, as I said before, are well defined, even if lambda is outside the G vector fan. Return functions are also well defined anywhere in space. And Theta functions, if you're thinking about cluster scattering diagrams, then theta functions are definitely on your radar screen. I don't think return functions are on anybody's radar screen particularly, and I'd like to maybe change that by putting in a shameless tangential plug to all the new work. But old work. The return function, if we're in rank 2, so this would be a quiver with two parallel arrows, two vertices and two parallel arrows, or affine A1 tilde if you like. And you do that return function for the limiting ray, then you get this thing that's a limit of ratios of cluster variables, and it's also like a generating function for the Narayana numbers, and it's kind of fun. But new is that there are analogous results in affine type, any rank of affine type, so not just rank 2. You know, in general, including in rank 2, but I don't think I thought much about it. In general, the return function and the theta function are related by a quadratic equation. Okay. Yes. It's really something. There's really nothing that shows up. It just it's like let's see. It's like the theta function is like the return function plus something in the y's divided by the return function. And then if you solve for the return function, it's this quadratic thing. Yeah, also new, some of these return functions resemble the irrational letters that people are looking for symbol alphabets and for scattering amplitudes. I haven't said anything about this, but somehow people who are trying to write down scattering amplitudes for particle interactions are seeing some irrational letters. And some of these return functions are the quadratic, irrational ones that they're seeing. Also new, in the surfaces model, these return functions, if you take the return function for a closed curve, what you're getting is the laminated lambda length of that closed curve. Now, so in the surfaces model, cluster variables themselves are like hyperbolic lengths. And so what we're saying is that, like, actually, if you take a closed geodesic in one of these hyperbolic spaces, that what's its hyperbolic length, it's basically a return function. And I should mention some things that are close. This ratio of cluster variables, this was also in Kontsevich and Schiffler. I have to give a lot of credit to Danny Kaufman about this observation in the surface model. He pointed it out in the simplest case, and that's the only reason I would have ever thought of it. But basically, the thinking, once you have the ratios of cluster variables, you say, oh, it worked for him, it works there. So you have to do a little bit more work to get it to work, because you can't always turn it into the simplest case. And then there's a physicist named Hendershey who is thinking about these return functions, and I need to understand more what he did, but he's talking about getting these irrational symbols from cluster algebra, from scattering diagrams. Okay, so apologies, because this was probably the least I gave you the least background about this slide, but just some things I wanted to say. And now let's get back to the main thrust of what we're doing. So theta function is an affine type. So let's start actually with finite type. Scattering diagrams in finite type. Well, what does finite type mean? Finite type means that there are finitely many cluster variables when you do your cluster algebra. In this case, there's also finitely many walls in the cluster scattering diagram. That's probably an if and only. That's got to be an if and only if. And all the walls have the simplest possible scattering term, and all the theta functions are cluster monomials because the G vector fan is everything. There's no theta functions outside the G vector fan. Okay, and I was wondering whether I would need that. I did need that because I didn't explain the picture. Okay, so I try not to ever count on my memory. It happening correctly in the moment. Okay, so what is this thing? Oh, he just drew a bunch of circles on the board, and then he said this is finite type something. Okay, so there's a G vector fan. It's a fan. This is an example where it's a fan in 3 dimensions, and so it's a simplicial fan. I mean, you can draw that in, Grant had cool drawings of this in, where you could rotate it and look around. I prefer to sort of just turn it into 2 dimensions by intersecting with a unit sphere about the origin, right? All the information still in the intersection with the unit sphere. So now I've got a collection of sort of great circles and arcs of great circles in the sphere. I do a stereographic projection. There's this great fact from geometry from I'm not sure how long ago that says if you project great circles stereographically to the plane, you get circles or maybe straight lines through the origin. And so that's what these are. So when you see this triangle here, sort of curvy triangle, what that is it's a triangular region of the sphere that corresponds to a triangular cross-section cone that intersected the sphere. Okay, so opinions can vary even among co-authors about whether these are good pictures. David Spire, when we were writing together, he always said, but yeah, but show me the picture that's not that. So okay. Okay, so that was finite type. What is affine type? What's a cluster algebra of affine type? So there's actually, I mean, in finite type, it's a structural thing about the cluster algebra. There are finitely many cluster variables. Okay. Affine type, you might be guessing that we're going to talk about, types of root systems or, extended Dinkin diagrams. Yes, but also affine type, once we get beyond 2x2 matrices, which are sort of a special case, a cluster algebra of rank greater than or equal to 3 is of affine type if and only if it's not a finite type, but it has linear growth. You can get this by putting together results of 7 and Felix and Shapiro, Thomas to Markin. So that's what it is. This is a sort of a class of cluster algebras that makes a lot of sense to talk about, even aside from wanting to talk about root systems and things. Okay, but a more constructive answer, and also where root systems come in, if I start with a Cartan matrix of affine type, and I put zeros on the diagonal instead of 2s, right? And then if I put signs off the diagonal, plus or minus, just change the signs off some of the signs off the diagonal, so that I get a skew symmetrizable matrix instead of, I started with a symmetrizable matrix, or maybe you just do symmetric and skew symmetric if that's more comfortable. But I sign it, and I make sure it's acyclic. I don't want, so even if I turn it into a quiver, I don't want to make oriented cycles, right? That's what affine type is. That you get something of affine type, and then if you are mutation equivalent to something that came from that, that's exactly that. And it's exactly parallel to the Fomin-Zelevinsky classification of finite cluster algebras of finite type. Okay, so we've got a Cartan matrix of affine type. If you like an extended Dinkin diagram, there's a root system associated to that, and there's an imaginary root which we'll call delta. And there's lots of imaginary roots, but there's one that's sort of the nicest one that we'll call delta. There's a Coxeter group, and the sign information that's in the exchange matrix that wasn't in the Cartan matrix defines a Coxeter element. Okay, so in affine type, the G vector cones cover all of space except for a codimension 1 cone that we like to call the imaginary wall, because it's a wall in a scattering diagram. But there's also this cone, it's outside the G vector fan, but there's a decomposition of it into cones, right? The maximal cones in this decomposition, of course, are codimension 1 in the big space because it's already a codimension 1 cone. And that combinatorially, that imaginary, the cones in that imaginary fan, they're combinatorially a product of cyclohedra, type B associahedra, if you like. All those imaginary cones, and all those cones in the imaginary wall, they're the star in this cluster scattering fan of one ray, which is called the imaginary ray. It's spanned by a vector nu sub c of delta. All the other rays in the imaginary wall, and also in the rest of the fan, are spanned by by G vectors of cluster variables. Okay. So nu sub c, what is this? I've suddenly started using nu sub c. There's a piecewise linear map. It takes roots to the things that are like G vectors. Okay. So here's an example. So this is like G2 tilde, if you like, but this is just the kind of thing that these things look like. It looks a little bit like the finite example, except there's this place where you have these cones that are somehow limiting to something, and the just point. The imaginary cone is between that vertex and that vertex. Right in the middle is the imaginary ray. Okay, it's a product of very small cyclohedra. It's one cyclohedron, and it's a 2 cycle. There's only two simplices in the cyclohedron, and then it's really the link of that one ray is the cyclohedron. Okay. if I go to rank 4, so now I'm in a 4-dimensional scattering diagram. That means my imaginary wall is 3-dimensional. And I'm going to draw pictures that are sort of its cross section as a cone, and it's the cross section of its decomposition. So if I have one cyclohedron that's, I guess, one 2-dimensional cyclohedron, then the cross section is just that cyclohedron. Right? Cyclohedron is a hexagon, and you can see that it's flattened out into a triangle, but there's 6 sides or 6 cones that it's broken into. Or I could have a product of two 1-dimensional cyclohedra, and they share that ring. Okay. There's more about this. So there's 3 roots that I'll call just beta 1, beta 2, beta 3. I apply this nu sub c map, but can I get rid of the nu sub c map? It's not good. I wouldn't want to write a paper this way, but for a talk, let me just pretend that these just are really just beta 1, beta 2, beta 3. And everything that I'm going to do sort of commutes with, not with leaving out the nu sub c anyway. So delta is the sum of these 3 things. The action of the Cockter element is cyclic on these 3 things. So also, it's a triangle, but that's because somehow the sum of beta 1 and beta 2 is just right on that line. So we're seeing it as a triangle, but there it is. Okay, so and so this beta 1 plus beta 2, for example, is delta minus beta 3. Okay, so now let me tell you some results about the theta functions. The philosophy here is that theta functions that are already cluster monomials are known. And it might be this is actually computation. This is reasonable in affine type, because you can, if you told me a G vector, I haven't implemented this yet, but you could write a program that would find you the cluster variable, and so you do it that way, and then you know what that theta function is. So theta functions that are cluster variables are known. So if I can write the other theta functions in terms of cluster variables, then they're known also. Okay, so here's the theorem. It says that if I want to know the theta function for this imaginary, that's the shortest vector in the imaginary array, nu sub c of delta, I'm supposed to multiply together these 2 theta functions, and then I'm supposed to subtract off some coefficients times other theta functions. Is it okay though if I just leave out the nu sub c's again? It's preferable maybe if I just leave out the nu sub c's. So I'm supposed to take, I almost want to say just beta times delta minus beta, which doesn't make sense, but like it's the theta function of beta times delta minus beta, times the theta function of delta minus beta. I'm supposed to multiply those together, supposed to subtract off these other things. And here's the picture, right? So if I wanted to know what the theta function here is for delta, I'm supposed to multiply these 2 theta functions. And then I'm supposed to subtract that theta function and subtract theta function, each with a little coefficient in the y's. Okay. But the point, just letting your eyes glaze over the details, is that this is a pretty simple way to get the theta function for delta from theta functions you already know. Actually, it's part of checking an example for the results that I shamelessly plugged before. I was just used this the other day. It's doable. Right? To check this, it really is the correct theta function for delta, because that checks out this way. Okay. All right, and I think I already said all the theta functions on the right side are cluster variables, so they're known. And maybe there's a way to say this that lets us pretend that we're seeing something in higher dimensions, right? This picture is really, you really are seeing a 3-dimensional picture that's sort of sliced onto a 2-dimensional plane. But if we just concentrate on the 3 corners of the triangle, in higher dimensions, there are, in this case, 10 vertices of a 9-dimensional simplex, which is the cross section of a 10-dimensional cone, and we could just think about, somehow putting them on a cycle, the way that, so that C, the Coxter element, just permutes them cyclically like this. And so what this is saying in that case is, okay, I've got beta, which is one of these single, basically simple root kind of things. Delta minus beta is the sum of everything else. And if I want to multiply, if I want to find out what the theta function of delta is, I just need to multiply these 2 together and then subtract this one and that one, and there's the y. All right. Yeah. Did I remember to say this? No, I didn't. Okay. So I'm 2 for 2 in doubting my future self, which is now my current self. Let's not get into that. No, I didn't remember to say. So the point is, I wanted to understand what this theta function was, but what I really did was multiply two theta functions together. So if I'm gonna multiply these two theta functions together, this is now a sum over all pairs of broken lines that satisfy certain conditions. And I guess if we sort of, rearrange this equation, I guess I'm finding that there were only three of them. Only three pairs of broken lines. And it's pretty easy to see what those pairs of broken lines are. Not all that hard to see that it really works, that they really are broken lines. But the thing that's really hard is why, this is even in this picture, I guess we'd be talking about a 10-dimensional scattering diagram. Why is there not some other broken line that goes way over here, bends over here, comes up here, does all these crazy things? How do you know? Right? If you're doing two-dimensional examples, then you could kind of just say, well, all the broken lines in this would push you in that direction. You could never get back, and you could say things like that. But in this higher dimensional thing, it's, how do I convince myself that there are not any others? And that's where a lot of tools come in, tools that cost me, maybe years of my life, even in the time of doing them, and also like probably taking years off the end of my life. It's in me. I'm sorry, that was getting a little personal. Let's get back to the math. Okay, so yes, I did now remember to say it's a structure constant calculation. Okay, but let's talk a little bit more. So if I want to find out, remember, I've got every integer vector, and I already told you how to find the theta function for the first, the shortest vector in that one limiting ray. What about 2 times that vector? Well, if I want the theta function for 2 times that vector, here I'm not going to get rid of the inductive c's, they're maybe not quite as bad without so much other stuff around them. I want the theta function for 2 times that vector in the limiting ray. Well, I square the theta function for the shortest vector in the limiting ray, and I just subtract off something with y's. And then for higher, if I want, k times that vector, well, I can multiply, the theta function for the shortest times the theta function for k minus 1 times it, and subtract off another theta function. And so this is sort of like a Chebyshev-ish recurrence. And in the cases where affine type overlaps with the surfaces model, this is something that was already known from the Musiker Schiffler Williams work on this. Okay, but it turns out it works in general affine type and using a really different toolbox. Yeah, questions?
Just to check, is it like the?
Yes, that's right. It's right in the annuals. This is the one closed loop. Yes, that's right. Or in the vice puncture. Yeah. Okay. So again, this is really a formula for a structure constant, right? How do I multiply this, k minus 1 times the vector theta functions for those. More generally, there's a formula. Actually, we worked out that this, you could, once you knew these facts, you could sort of recursively prove these facts, but also you can get them directly with theta, with just broken lines, telling us how to multiply different multiples of this one vector to get theta functions. Okay, so what do we know so far? We know there's this imaginary cone, it's codimension 1. There's one ray in it that's not a G-vector fan. We now know all the theta functions in that ray. We know all the theta functions for the G-vectors that are on the relative boundary of this cone. So we're done, but not quite, because we need to know that, what happens if we're in the relative interior of one of these imaginary cones. Well, it turns out that you can, once you've found the theta functions for the rays, it's just multiplicative inside them, right? I mean, if one of your rays is this imaginary ray, yes, you have to do Chebyshev when you multiply. But then if you found this vector, if you can write, your lambda as a sum of vectors where all the lambda I are vectors in distinct extreme rays of the cone I'm talking about, and I know those theta functions, I just multiply them. So somehow, maybe a different way that I could have written this, it could have looked like a linear combination of shortest things, but I'm not assuming these lambda I are shortest things in their rays. They're just whatever multiple of that shortest thing. All right, and so I need to know that theta function. I can get it because I know that theta function, that theta function, that theta function, and that completes the description. So now we know all theta functions of affine type. Questions? So one more thing I want to say, but it's a good place to pause. Yeah.
Can you just said about the things in the relative interior? So this is the statement that we just know if it's in the G fan,
That's right.
but because there's something imaginary, we like, a priori know nothing.
That's right. We don't know. Yeah. I mean, yeah. And you sort of know it in the surfaces model too, because somehow these would be disjoint things, and that's sort of maybe the definition of multiplying disjoint things is you just put them together and that, yeah.
Do you have any thought about if this is like a special to affine type phenomenon or should hold?
That's a fabulous question. I would love to think that there's something that says once you know this fan, you just need to know what happens on its rays. I don't have any sense of whether or when that's true outside of surfaces at in this case. Other questions? Right.
Maybe hold for any finite mutation then.
Yes, it does. So that's right. Holds for any finite mutation type and anywhere inside the G vector fan. It's just, just because in finite mutation type, oh, sorry, excuse me, finite mutation type, pardon me.
Yeah.
Are you asking or saying? Whether
It's kind of a natural guess.
I-
Holds for surfaces and for.
I think that that's probably the right guess. Yeah.
That's probably what Melissa.
Yeah, finite mutation type problem. Yeah. I mean,
The point is that like everything is captured once you know these extremal. That way, right? And in general, it's just false because there is stuff like deep in the bulk.
Yeah.
Outside the TIDS code, so to
yeah, although at some point, maybe it depends on how you define the fan at that point, but yeah. Maybe your fine, I would just say your fine is your fan is very, very fine. So everything's a ray in the Badlands or something. So, but that's maybe I'm splitting hairs. Yeah, okay, so let me talk about imaginary exchangeability. Actually, one thing that in connection with Sergey's question that in the very long-winded abstract I said, but I don't even have time to talk about here about that. But my sort of thought is that eventually finite mutation type, all of them will be this well understood. I think we're eventually going to do that. And it's just, we're down to some, short list now. Anyway, there are some cluster variables that are exchangeable in the cluster scattering fan, even though they're not exchangeable in the G vector fan. And we'll call those imaginary exchangeable. And what in the world is exchangeable? Let me show you an example. I don't know if maybe it's something you talked about, but in this fan, I'm just going to point. In this fan, right, here are two clusters. This part is G vector fan. So here's two clusters. They share this edge. If I took this one out of that cluster, there's a unique one I could put in. These two are exchangeable, right? But these two, they're exactly two G vector arrays that are in the imaginary cone. It's these two. This is something else. This is the imaginary thing, but there's these. There's no cluster, there's no triangle that I could take this one out of and put that one in. However, in the imaginary cone, there is a two-dimensional cone here, right? Because we're slicing, it's a two-dimensional cone. If I take this one out of that two-dimensional cone, I put the other one back. So these are imaginary exchangeable, right? They're not exchangeable in the G vector fan, but they are exchangeable in the sense of this bigger fan. Okay. Here's another example of it, right? I wish I could see 4 dimensions, but this is a 3-dimensional cone, and it's sitting inside this big 4-dimensional cone that I can't quite imagine. But these two, I mean, they're exchangeable in this. These are the imaginary cones. I can pull this one out, and the unique thing I put back is that one. There it is, right? But in the G vector fan that's around this and higher dimensional, there's no way to exchange them. Okay, so that's what imaginary exchangeable is. And the theorem is, well, first of all, there's an older theorem that just says, what are the imaginary exchangeable pairs? Let me get to that in the example. We know what the imaginary pairs are. And also, let me have you just not think about this, the definition of phi and phi prime quite yet, because the picture will be better. Okay, there's, the point is, if I multiply these two, this is like an exchange relation, right? If I have two exchangeable cluster areas, I multiply them together, they're equal to some sum of things. That's what, that's what an exchange relation is. Well, if I multiply these two exchangeable theta functions together, I get this thing. Let's get rid of the u sub c. Delta's here. Right? So this is like a delta minus beta. Beta is one of those extreme points on the imaginary wall. So and delta minus beta prime is the other. That's the condition that beta and beta prime have to be in the same C orbit, but then this delta minus beta and this delta minus beta prime will be exchangeable. If I multiply them together, well, I get something. Let's look at it in the picture. Okay. So here's beta down here. Here's beta prime. in sort of circled in these two pictures as delta minus beta and delta minus beta prime. If I multiply those together, I'm going to get, well, this product of thing, well, let me just tell you what the phis and phi primes are. Phi is like if I started at beta, I have this sudden fear that I did this backwards, but I'm going to just say what it looks like. If I started at beta and do C, I do have this backwards. If I start at beta and do C, how, what are the things in between beta and beta, right? C is the rotation by one step. So theta somehow, or phi is, I think I did backwards, my apologies, but phi is somehow the stuff between beta and beta prime on one side, phi prime is the stuff between beta and beta prime on the other side. And so it's saying, I can write this as not a sum of two things, but as a sum of three terms, where I have theta functions for these phi and phi primes involved, also the theta function for delta, et cetera. Okay. If I just restrict my attention to theta functions that are in the imaginary wall, so not just the ones that are outside the G vector fan, because some of them in the imaginary wall, there's those edges, that there are those extreme rays that are in the G vector fan also. But I want to take all the things that are actually in the imaginary wall, and just multiply them together, let them generate an algebra. They don't bring in any of the other theta functions. So there's this this subalgebra, the cluster algebra, that just has to do with the theta functions from the imaginary wall. Combinatorially, the imaginary wall is a product of cyclohedra. And the theorem is that the imaginary subalgebra is a generalized cluster algebra, a product of type C generalized cluster algebras, right? Type B and type C, if you're thinking about Cox groups, are the same thing. So maybe we should have been saying type B, type C associahedron for cyclohedra all along. But anyway, details here, it's the Chekhov-Shapiro definition of generalized cluster algebra. All the exchange relations are just ordinary exchange relations in the cluster algebra, except for that one I just showed you, the imaginary exchange relation. Okay, so I've got like very little time here left. Let me just say a few words about tools. The construction of cluster scattering diagrams in affine type, I should have said in affine type, it uses double Cambrian fans. So there was this Cambrian fan idea in finite type. You need two of them, two opposite ones, to get the whole G vector fan in affine type. There's an almost positive roots model in finite type that Sergey and Andrei came up with. There's a model that works in affine type also. And you need shards because your walls are going to be shards. And I don't have time to say what shards are. I'm trying to think if Grant said that word. Can't remember. But then to prove these theta function results, you need additional tools. And the point is, as I've said before, to compute a product of theta functions, we need to somehow find all pairs of broken lines such that, whatever. How do you know you've got them all? So the biggest problem is, how do I know I have them all? How do I just rule out lots of other things? And there's some tools here. Let me actually say, I think I'll just have time to just say something about the first tool and then I'll stop. I'm conscious of not wanting to win the longest talk award. So combinatorics involving a Coxter element in affine type, whether it's non-crossing partitions or cluster algebras or something, there's always this piece that's type C, or that's a product of type C. Arguably the first appearance is like the tubes that come in up in AR quivers of affine type, if that's something you've seen. But those tubes at the bottom, the combinatorics is cyclohedra. So that's type B or type C combinatorics. More recently, McCammon and Solway were taking non-crossing partition post sets, and they weren't a lattice in affine type. They put something in, to a finite number of things in. What they put in was sort of like, they joined in this product of what they were calling type B non-crossing partition lattices. Type B and type C are the same thing in that context. But finite type B things. And also, type B associahedra, they appear, well, I mean, those pictures you were seeing where I drew like circles of dots, that's the cyclohedron model showing up. Neighboring seeds are further development along these lines. And let me just actually, let me just cut to the picture quickly. You can find a choice of seed in affine type where the imaginary cone is cut into cut into smaller cones, right? In a way that's not just combinatorially type C, but metrically type C. And once you have that, then when you're doing certain mutations in the cluster algebra of affine type, you're really secretly doing these finite mutations in type C where you know everything. And that's, so you can sort of turn your problem into, I just need to know something about type C. So that, I think actually, maybe if you don't remember anything else from this talk, just the idea that somehow affine type, if you're doing something that could be cluster algebra, or if there's a Coxter element involved somewhere, type C is involved, finite type C, and maybe that's a method. Let me, I think, stop there and just ask a few. I brought, did I over prepare it? Okay. Yes.
Any questions for Nathan?
Yes.
Can you say anything about what this idea of imaginary exchangeable looks like in the quiver for that one? Or
That's a good question, but it's not a question that I know the answer to. Because, so, I mean, I don't know if this is an answer or not, but if you want to do that exchange relation, like, you know, really go from this cluster variable to that cluster variable, there is a sequence of mutations, a finite sequence of mutations you can do in the quiver. And I guess, now I've written, my brain doesn't do quivers as easily as it does change matrices. I'm not sure why that is, actually, because their quivers actually sort of seem objectively easier, but okay, whatever. But there's a finite sequence, and so that is written down. So you know, if you wanted to do that type C exchange, you can actually do it in the and that's why some of these things work. I don't know if that's a very good
is it
answer.
about like going around?
Kind of like that, yeah, exactly. You have to kind of walk around. Yeah,
Can you
exactly.
see the type C thing in the matrix? Like the imaginary thing?
Yes, in the exchange, that's probably better. Thank you for asking a follow-up question, which leads to a better answer to your first question. Yeah, there is a piece that's sort of, it's like, you can see it, it's type A. There's like, it's really a type A piece, but then you're supposed to scale something to turn it into type C. And it is kind of really in there, yeah. Yep.
So the set of broken lines that corresponds to computing the theta function depends on this choice of point in the first quadrant.
No, it's actually, no, it's independent. You can, oh, sorry, so the set of broken lines, yes, yeah, the set of broken lines, yes, sorry.
Yeah, and I guess I'm not sure how interestingly this changes in affine type, but I'm curious if your methods kind of capture this dependence at all, or.
I would say basically, no, we really just wanted to find the theta function. We did, I mean, at some point, part of ruling out the last possible broken lines to say, oh, but I'm going to put my point over here. We didn't think about, you know, varying that and all. Oh, but we were just so pleased to be able to say there are no more, right? If we, as long as we put the point here. So, but there might be something interesting to think about there. Yes.
So I'm not sure, I think the answer is not really the picture. So you say combinatorially it's a product of type C. You said that you choose properly something, then it's really geometrically type C.
Yes. So there's something that's swept under the rug there, which is, okay, so it's a codimension one cone. If you choose the right initial seed to look at, then that imaginary wall is a half hyperplane. And it has the structure where if you look in its boundary, that is metrically type C, or metrically a product of type C G vector bands. And then there's the imaginary ray going off. So it's like a product of like this ray with that type C thing. Does that help?
Yes. So can you choose the seed differently so that what you see is really the type of hidden and the graph as I said. And it would be, can you change seed so that you go from one to you can understand why there are two very different realizations of the cyclohidden. One is really type B or C as a cyclohidden, and the other one is when you realize it as a section of the type A as a cyclohidden, or as a cyclohidden like the graph as a cyclohidden.
I mean, what
have something which goes.
I don't know if this is an answer that you'll like, but I mean, one way to answer that is to say, if you take an acyclic initial seed, it will force you to think about the cyclohedron realization. And if you take one of these, what I'll call neighboring seeds, it will say, oh, but actually it's metrically like type C G vector. I don't know if that, and it's kind of related to the other questions, right? Like you can do any mutations in this type C by walking through the affine.
Any more questions?